Good morning, everyone, and thank you for joining us. My name is Dean Lees, and I'm a member of the technical sales engineering team and marketing team here at Buckley Associates. Uh, Today, we're going to be talking about, for quite a while, actually, we're going to be talking about the design of chilled beam systems and how to properly design and think about chilled beams within high-end building designs. And with me today, I have a couple guys, Chris Burrows, the product manager for Stratified Air Systems, and Nathan Vaughn, a product application engineer on the Beam team. Also not listed here is Ed Fruth, our Northeast regional sales manager from Price. And before we get going here, I just wanted to say a few words about what we're going to be doing today. And really, this is a deep dive into chilled beam systems and how to think about chilled beam systems. We've kind of at Buckley over the past few years focused in on some key markets and developed these types of workshops and where it all comes from really is the Price engineers training. And we take what we would normally cram into 2 hours and really, um, rather than doing an overview and a 30,000 foot view, we take an entire day and we run through the system from the piece of terminal equipment up to the considerations at the air handler and elsewhere within the building. So we kind of try and take a holistic approach and a system design approach to thinking about these things. Even though we're talking primarily about chilled beams today, we really want to discuss how to design these systems as a whole. And we started with this a few years ago, as I said, with a lab design workshop where we talked about the valves within the space, how to control the space, and then we went up to the roof and talked about the fans and the makeup air units that tie into those systems. And then we did one on GRDs as well, and how to properly design air distribution. And now we're going with our third workshop here with chilled beams. And although Boston is a heavy chilled beam market, and we do see a lot of that type of work up here, I think there's still a lot of still a lot of misunderstanding or almost fear when you get into a chilled beam system, and a lot of people shy away from them due to the complexity. There's as engineers, we tend to be more comfortable with more traditional type systems. But in our market, and especially with energy code trends and things of that nature, which we'll talk about later in the day, chilled beams are always a great approach to get that efficient system design. And if you know how to approach the design, it becomes a lot less intimidating. Really tend to find that it's really not all that complicated. So I thank you all for joining us today. I really hope that everyone finds these sessions to be informative. I really appreciate that you've committed 5 hours of your day and 5 hours out of your busy schedules to be here with us today and learn some new things. And we do have quite a few people on the line here, so everyone will remain muted throughout the duration of these sessions. But we have 5 people in the room here that are chilled beam experts. We're here to answer your questions. If you want us to spend a little more time on certain topics, we're more than happy to do that. Use the question pane or the chat function within your GoToWebinar toolbar and reach out to us. We're going to be monitoring that all day. We'll address those questions as they come up. we'll spend more time on certain topics if we hear from you that that's what you'd like to see. I really want everyone to get the most out of this that they can. So, thank you to Price for being here, for helping us to put this on. And again, thank you all. And with that, I will hand things over to Chris Burrows.
All right. Well, thank you, Dean, and thank you to the Buckley group for arranging this again, and for everyone joining us. So my name is Chris Burrows, and we're going to be going through this next section. Let's see. There we go. Sorry about that. So the next group of presentations, at least for the morning session, we'll have a couple of people jumping in to discuss a range of topics. Myself, Chris Burrows, Ed Fruth, and Nathan Vaughn, we're from Price Industries, and we'll be touching on a range of topics from the introduction to chilled beams. Hopefully everyone finds that of interest and learns something new from that session. But it's a bit of a primer on the system and components involved, what a chilled beam is, and then what are the resultant benefits. And then we've got Ed and Nathan who will follow up on some really neat topics that are really helpful going forward. So again, this is the introduction to chilled beams. Again, I've been with Price for about 9 years and graduated from Georgia Tech. I am located in Georgia, just outside of Atlanta, and get involved in ASHRAE at a national level, and involved in research projects and developing product for Price Industries. We call it the Sustainable Systems Division, which essentially encompasses chilled beam technologies, underfloor and displacement ventilation. And I've been involved with those since the beginning, joining Price Industries. I love traveling and hiking. The photo there at the bottom is taken from Ireland when we went there in 2018, and was absolutely a fun time. Love experiencing other cultures and getting outside as much as you can. So thought we'd do a little get to know, since we're going to be spending a lot of time together. And in fact, that's related to the next portion of this presentation. In the intro is kind of, just as a meet and greet, getting to know chilled beams with Price Industries, just where we have our facilities manufacturing located for these products, and also some of the test chambers and mock-up spaces that we just want to offer out there as you come into discussions on new projects with perhaps clients that are not familiar with these technologies, and getting them into the tech centers and research centers to kind of witness, touch and feel, and see the smoke demonstrations is just invaluable in kind of working through that initial discussion on these projects. And then we'll go through the basics of chilled beams, what it is again, and the benefits of that, and then common applications or case studies that we've seen out there, and talk through that. So the first one up is, again, Price Industries, who we are, where we're located. The bottom right cluster of plants and facilities that we own are down in the Atlanta region. That's where Nathan Vaughn and myself are located. And the Suwanee location is where our corporate headquarters is. And we're actually in that Crestridge facility, is the top one in that cluster, is where we manufacture the chilled beam equipment. And then out in the Winder facility, we actually make our own water coils, which we'll talk about that in a little bit. There are several tech centers that we have throughout the country. And again, that really we offer to be utilized, and that we could be involved in hosting you as we as you come up on projects, we're happy to do that and perform mock-up tests and various things as needed on projects. Price Research Center North is the testing facility, really the mothership of where we do our catalog testing and extensive testing up there. That is located in Winnipeg, Manitoba. And the PTC is again located in Suwanee, and then the PTC West is outside of Phoenix, Arizona, in that location. So we actually just recently moved to the Crestridge facility and opened up this 100,000 square foot factory to manufacture noise control products, so silencers, attenuators, panels, as well as chilled beams and underfloor air distribution products. And we're already out of space, so we're planning another 50% expansion or addition. You can see that the land up there in the sort of the northwest picture side, and we'll essentially be finishing that out hopefully end of 2022, so we can expand the lines, increase our fabrication capacity, and as we build for the future. Within this factory is an additional powder coat line that we put in there, mainly for painting various products, underfloor, acoustic panels, but really the high volume is painting the chilled beams, products, plenums, and you can see it in the bottom right there. We've got our standard B12 unit going through there with the chilled beam getting painted. So we can do an automatic manual application. There's even another booth for special paints that you can run separately from the standard powder coat finish. So we're really excited about this. You can see on that in the left kind of back behind the assembly line, that large enclosed space, which is the powder coat room, which essentially has to be a separate conditioned chamber, which is again really neat part of the system. But right off of the paint line, products, the pieces come off and just are pulled off right onto the assembly line. So really just an effort to try and improve capacity and efficiency. And again, we're really excited to be expanding like this. Now moving back up out of Georgia up to Winnipeg, we've got again in the Price Research Center North, the hydronic test chamber, which is roughly 200 square feet as the footprint. And this was really designed initially as a walk-in cooler and then built up from that with radiant surfaces, radiant panels all throughout the interior of the space, so we can tightly control the surface temperature and to a high degree of accuracy test the finished product, but with the coils and the performance of said products such as chill beams or radiant technologies that we get into. And so this is where all that catalog performance data that is available online and that you're using is coming from. So we're also heavily invested in vertical integration as really an effort. You see this nowadays really coming into play with lead times and various supply chain issues. You know, we've started many years ago trying to invest not only in our anodizing tanks, which we use for our bar grills and various products, to essentially have that in-house and not have to send it out for extended lead times or have that part out of our control, and also manufacturing our water coils for the chilled beams. And you can see that vertical mechanical equipment there that manufactures the water coils for our chill beams. So really all of that comes into play to just helping provide effective service to the industry. And so the last kind of part of this, I wanted to show a timeline starting in 2007. That is when we constructed the hydronic test chamber, and that was quite an effort in a pretty extensive project. We went over to Europe several times and investigated the labs and test chambers that they have over there that have been sort of in use for chilled beams, radiant products, and kind of used that experience and knowledge that they've had over the years to build our test chamber. And we've each couple of years we third party test and validate our test chamber and instrumentation to various highly regarded third-party labs. In 2010, we started manufacturing our own chill beams and have done so throughout up to year to date today. And we were heavily involved, as you can see in the bottom there. 2012, we started engaging with ASHRAE. Several people from the price side were involved in building the ASHRAE 200 method of test for chilled beams, which our chamber is approved to test to. And that is kind of an important note to make sure that, as you're looking at performance, just ensuring that across the different brands that everything is tested to ASHRAE 200, because that's really important to ensure you're getting, real results there. So the next couple of slides, I just wanted to mention some educational tools or opportunities for PDHs and learning opportunities. So we've printed a number of handbooks, and if you don't have a physical handbook and are interested, certainly reach out to Buckley or us to get a copy in hand. This is a really good resource, goes back through even control theory and psychometrics. It's really, as we haven't seen much of a match as far as a reference out there in the industry that encompasses all of this info in one book. And there are a couple of chapters on chilled beams that would be useful as we go throughout the day. There's going to be other examples that we don't cover due to time, but that can be in there and very helpful to you. It's also available since 2016 in a digital format, and so you can log in there and essentially sign up for that, get the digital version, and take quizzes on each chapter. And that if you did the entire book, which would be incredibly impressive, that would total about 66.5 PDH credits. So if you're getting behind in a year and you need some easy credits, this is a good way to do that. And then lastly, I don't know how many people listening in are aware that this is also something available in the public domain, but the Price Learning Portal is something we kicked off this year, and it basically has every webinar and digital presentation content that we've done over the years. It's in the newest format, and it's on this Price Learning Portal, and it's all combined into these sections and kernels of topics that you can go through. So, for example, you'll have an entire day or two of content on sustainable systems. You can go in and look at educational facilities and learn all about each type of system that we offer and talk about the design of those different technologies just on educational facilities. So it's a really useful tool, very intuitive based on feedback we've had from various clients. So would suggest peeking into that and checking it out. All right, so next we're going to move into the basics of chilled beams. Of course, we have to, before getting too far, define what a chilled beam is. And it is a sensible only device that contains a water coil within the unit itself, up there kind of concealed in this photo behind the per face. And it uses chilled and heated water supplied above the room and above the room dew point to cool and heat this space in which it is installed. And it's basically a decoupled system that uses the primary air. And you can see on the chill beam image on the left, the duct collar on the side. Essentially, that has a connection. So the primary air, which is your ventilation and latent load air from the DOAS or package unit, that is taking care of all the latent requirements for the space. The rest of the load, the sensible load, is really taken up by that chilled water or heated water coil within the unit. So that's basically what a chill beam is. Now there's various versions of it, and it has evolved over the years into several sort of main types of chilled beams. The first one and most common one is the active chill beam, and the active portion of that is essentially the primary air component, the fan forced supply of the primary air pushed into that chill beam plenum. And so that is what essentially creates the induction. We'll talk about that sort of science in a slide or two. But essentially, this is an active beam, meaning that you've got a primary air supply to it, and there's a fan sort of pushing and creating the static to push that air into the beam. Floor-mounted chill beams. This is a unit that is really neat in that it creates a displacement style airflow in the space. But as you can see in that sort of oval sized geometry inlet, where you still have that primary or ventilation only air running through the building and connecting up to that unit, and then the induction through the coil is kind of pulling in the room air and creating the rest of the air changes in the space. But the discharge pattern creates a very similar distribution compared to an all-air displacement system, but you get a lot of the energy benefits by pushing that sensible load to a coil in this space. So we'll talk about that in a little more detail. And then you have passive beams, which is kind of sort of the initial creation of a chill beam, different from radiant panel in that it's less of a radiant component and really driven by natural convection with the warm air getting up behind the coil and cooling off, and then it essentially falls down due to being more dense down into the space through that perf face there that you see. So that does not have a air connection from a fan unit on it. So that's operating simply on natural convection. You typically will get up to 400 BTUs per foot with a passive beam, whereas with an active chilled beam, it's not uncommon to see up to 1,000 to 1,200 BTUs per linear foot based on the selection and the requirements of the building, so you can get quite a bit more out of the active beam. Okay, so how does it work? What is if we peel back the curtain, how exactly is it achieving the same amount of conditioning to the space with much less airflow? The unit basically operates on induction, and the equation here is showing that our total airflow is a combination of the primary air added to the induced airflow component. So we can see in this example, the IR, or induction ratio, is 4.0. So we have 4 parts of induced air from the room to every 1 part of outside air. So say for a 4-foot unit, we've got 50 CFM of outside air, or primary air, that is being supplied through the duct into the unit, and that's pressurizing that pressure vessel up above the nozzle plates that are being called out on that right photo. And then you have essentially 4 parts, 4 times 50, which is the induced airflow, which combines to equal 250 CFM, that total airflow that is being supplied to the space. So what is happening is again, you're pressurizing that plenum, which is, and it's usually around 0.5 to 0.8 typically of inches of water column is the pressure within that plenum, and it's pushing the air through the nozzle plates. So there's a bank of a bunch of nozzles that are pushing the air at a high velocity through the discharge, and what that creates is a low pressure zone above that water coil, and it allows the room air, so right about here, it allows the room air to be pulled up through that coil, through that induction process. And so the warm room air is going to come up in the case of cooling and cool off through that coil, and then be supplied out through the discharge into the space. Now, in the case of the displacement active chilled beam, so this is floor mounted up against the wall, usually at the perimeter wall location, and can have a cooling and heating component to it. So again, that primary air is down in the bottom and back section where you might have the ductwork running down from the ceiling and connecting up to the side of the unit. And that's pressurizing the plenum. And this also has nozzles as well that helps induce that room air and pulls that through the water coil. So it's a very efficient type of approach. You've got the sensible cooling component within the space itself. You're taking care of the loads based on a zone requirement. And in this case, we've got a fin tube heater, which you can either have heating options for, 4-pipe water coil, or a fin tube heater, which is what's shown here. And as we all know, that fin tube is a pretty effective way to heat through natural convection. In this case, you do not have the active nozzle portion around the fin tube area, so that's just going to kind of kick on, open the water valve as needed when in heating, and allow the space air to kind of pull through that perf face, heat up through that fin tube, and rise up to condition the glazing requirements. So again, in today's world, the ability to squeeze out the energy, but also provide a displacement pattern airflow in the space. I'm not sure how many joining us today have researched up or used displacement ventilation, but it is essentially an air system that is not driving the air momentum in the space by a ceiling diffuser. Instead, it's just kind of trickling out at low velocity. And the thermal plumes in the space generated by the heat loads, in this case, it'd be students or a teacher or computers at the desks, that's warming up the air around them, and that warm air in a displacement stratified system wants to rise up naturally. So, contaminants, things from breathing associated with thermal plumes or the heat loads, in the case of an occupant breathing, a lot of those contaminants are effectively pushed up and displaced to that upper zone instead of mixing everything uniformly throughout like a dilution system. So this is a really good opportunity, not only for new construction, but also if you have a lot of retrofit projects, upgrades from various stimulus packages and government stimulus that schools are looking to upgrade the system from, say, an old induction unit. Those need to be replaced. This is a really good option to get a more efficient type of product in than the older types of products, and also upgrade into a displacement style airflow pattern. And then again, so the passive beam is essentially operating on a buoyancy differential, temperature differential, and you have a requirement of space for the warm air to rise up and move across that shroud and get up behind the coil itself. And then the warm air cools up as it sees the surface temperature, cooler surface temperature of the coil fins, and that causes it to fall down into the space. So location and placement is important, but you can essentially place that in hallways, around the perimeters. We've got a couple of case study that we're going to show a photo of an installation where they've done just that. But it's a really good way to get sensible cooling and a boost without necessarily an air component to it. And it works well with not only mixing with the various other active chill beams in the space, but even if you have a stratified air system with displacement in-wall diffusers or underfloor floor diffusers, you can still use this. And in fact, you get a bit of boost in capacity when you're stratifying. You've got warmer than set point temperature up above that ceiling space. So you've got 80, 85 degrees air across that coil, and you're cooling quite effectively in this manner. Now the real basics of why we have achieved such good energy savings with chilled beams is that we're reducing, again, the ductwork and the amount of air we're using to transfer energy throughout the building, down to basically your latent requirement or your ventilation requirement in the space. So that's going to obviously downsize the horsepower required, the fan energy needed to use to move that air in the space. And you're shifting that over to pumps and over to the water side. Not only is that quite efficient in terms of moving that fluid around in the space using water, but also water is much more effective at transferring energy throughout the space, and about 600 times more efficient at transferring energy. So those two main components combined allow us to achieve 30 to 33% in the case of office and healthcare. Now with healthcare specifically, in acute care patient rooms, as approved by ASHRAE 170 standard for healthcare applications, the total airflow can be with a chill beam combined with the 2 air change minimum ventilation requirement and the other 2 to 4 air changes induced at the chill beam within the space can actually combine to get your total air changes for the room. So there could be quite a significant energy savings in BTUs per square foot savings by going that route with a chilled beam in patient rooms. Now, in the case of labs where you have specifically a dry heat, very sensibly driven spaces in labs, and you can really save on a lot of energy for the same reasons we've talked about with offices and healthcare, but just to a higher degree. Now, with labs, it's important the placement of the beams, whether they're over benches or the aisleways. There's a number of considerations there, but just ensuring that with labs, if you have a lot of fume hoods, that can be complicated, but if just making sure that you're not disrupting the fume hood design, or if it's a teaching lab with one fume hood or a lot less fume hoods, that there's no air collisions between the beams if you have a lot of ceiling space taken up by them. So in terms of energy savings, Oracle Waterfront is a good example of this that was finished just a couple of years ago. And they achieved LEED Gold in the space and just over 30% savings over the baseline case in that area. This is located in Texas. Now, the fan energy savings accounted for 23%, almost a quarter of the building energy savings. And that with chill beams, because we're not moving necessarily a lot of air through that ductwork, and of course sizing the inlet properly, it's really a quiet system. There's no fan components or moving components other than really just the water through the coil and the water valve. So what they ended up in this case adding in is a white noise speaker system throughout the area because it was such a quiet type of system. Now, as we move into the discussion of reducing the sheet metal footprint and the costs associated with that change, we're going to talk about a Johns Hopkins hospital study that was done several years ago now. And what they basically looked at here on the left bottom photo, you can see there's 3 duct runs, 3 duct supplies up in the ceiling void. And so you have obviously a supply, return, and exhaust, and then the hot water piping for heating the spaces at the VAV. And then on the right side, you can see the chill beam system that they analyzed, where we not only reduced the diameter of those mains quite significantly down to 7-inch diameter connection, at least on the branch offs to the chill beams. And then we added in chilled water, but notice that there's only 2 supply ducts, or sorry, 2 duct runs. And that is because you have basically just a supply and exhaust into the space. For chill beams, you don't have a return because you're not, in this case, we're circulating any air back to a top unit, mechanical unit, and then we add in the chilled water supply that goes to the beams. So essentially, when they looked at a typical layout with the mixed air ceiling system, sort of the traditional approach that they've been using, you can see that we've got a ceiling diffuser kind of off from around the patient bed, and then exhaust in the bathroom with patient facilities. But in the top right, you've got the 3 duct shafts in the room, and enough space for the duct to run out of the room through the corridor, the ceiling space. Now, when we shifted over to a chilled beam approach, they were actually able to convert that space, shrinking it down enough to add in a whole nother patient room bed into that floor. And so this was a multi-story building. And so what they found in the financial side of things, considering how much dollars per square foot a hospital earns in revenue, combined with the operating cost reductions by using the more energy efficient chilled beam system, they were receiving about $18 million dollars per year increased revenue rate with this type of approach. There's also other first cost savings associated with it, not only on the mechanical system side with reduced ductwork, smaller mechanical equipment or DOAS units, but also the facade savings if you're designing the building from the ground up based on the type of technology you select. By shrinking that ductwork, you could really shrink the interstitial space or ceiling void that the ductwork is being covered up with, and that can result in facade savings and saving on material costs, which can also help on the first cost. So in terms of the benefits, we talked about a number of them. The last one, just wanted to point it out here in terms of maintenance. Again, there's nothing really complex, as Dean mentioned, with these components. There's no fans or complicated controls necessarily needed for these products. Really, you're just modulating a water valve to maintain space set point, and then just ensuring that the system is maintaining the humidity in the space, keeping chilled water above dew point a degree or two, really is what you need, the basics of a good operating chilled beam system as far as the space control goes, but very low maintenance. Now, as we move into applications, I just want to mention a couple of case studies and kind of show you how the various types of products have been applied in the space. And so before we move further, I know I mentioned three main types, or high-level types of chill beams, and that's the top three shown there. And then the bottom ones are just kind of variations of that. So the ACBM is a modular beam that has a four-way discharge and essentially helps reduce the throw out of each side of discharge from a traditional ACBL linear beam. So it's really perfect for small offices, breakout spaces, conference rooms, to get you really good coverage in those types of spaces. And then the ACBR is a good way to have the recessed unit hidden behind different grill types and into soffits that we'll show you a couple examples of coming up. So these are all dry coil, sort of 58-degree water temperature supply types of units, but there's also various induction units available that, again, when we say induction units, many people might think of the older units, but this is kind of taking the new chill beam design approach and sort of including drain pans to catch the condensation. If you're using a low temperature water supply in the space, there are options for providing these units with condensation management. So the LIU, which Nathan Vaughn will talk about in a little bit, is an A-frame design that is really neat, and it's an effective way to catch the condensation in the space. The one thing I want to mention on the ACBR unit is that you can only do the low temperature design with a vertically mounted style of ACBR. Horizontal is a bit more tricky because you can't put a drain pan effectively under that horizontal unit. In terms of an office space, we want to talk about the Children's Hospital of Philadelphia. So this is a project. This photo is taken from a campus building that we did several years ago, and we're in the middle of supplying their other facility with several beams. And what they did here was a two-pipe system in the interior space. So these beams here above the workstations are actually just a two-pipe approach for cooling. And then at the perimeter, if you can see my cursor, we've got these dual slot diffusers installed in the hard lid ceiling. And that is a ACBR, the vertical discharge. And what's happening here is there's a little bit of a reveal or a gap in between the mullions and where that hard lid ceiling starts. And so the warm return air from the glass, from that perimeter, is being pulled up through the ceiling and cooled and conditioned through that ACBR unit that's concealed and up above the ceiling, and then supplied into the space. So that has a 4-pipe arrangement along the perimeter to accommodate heating and cooling. So here's kind of a snapshot behind what's happening in terms of the framing and how an ACBR is installed and mounted in the ceiling. So there's really, in terms of the discharge, actually backing up from there, the ductwork is installed and connected up to it. That can be provided from the factory. And then you can essentially provide any sort of discharge type of slot or grill register connected to this unit, basically to suit the architectural needs in the space. It's just important to keep in mind, really staying above a 50% free area of the grill type, so that way we achieve proper performance. So this is another example of actually an exposed ceiling, at least along the sort of the perimeter area. You can see the exposed concrete slab, and there are ACBR units located up in this behind this perforated ceiling soffit here. So this particular discharge grill is using a linear bar type, as well as on the intake of the return side, which is the horizontal bar grill shown there. It's a bit harder to see. Hopefully, being that you're at the computer screen, you can kind of see the exposed linear beams with the Coanda wing option. So you can add wings, even if in most cases we're installing the linear beams flush within a T-bar ceiling. So you have that horizontal surface for the air to kind of hug against and have that create the Coanda effect. But if you have an exposed style approach, you can introduce the options of the wings to help keep the throw horizontal in an space, an exposed application. So here's another example of showing the ACBM in the center there, as well as a horizontally mounted ACBR unit with a dual deflection louver grill. So this is a project that we supplied locally using the ACBC unit. Even though we have a continuous look throughout the perimeter with the several basically perforated face along that perimeter, you really only need about 2 to 3 units, 4-foot section units to be active. So that's about a little less than half of that perf face that we're seeing from the space is actually active. It has a beam behind it. Otherwise, it'll be filler sections. And you can see in this case, we've got the ductwork is coming down from the sides, from the ceiling through this drywall chase on both sides. There's also some additional options there. We can even provide from the factory painted to match the chill beam, as well bookshelves and duct covers, inactive sections, which we had shown on the previous slide, to really provide any sort of option needed for that along that perimeter space. So again, as you move into an open ceiling application, there's a number of options to still achieve proper comfort and mixing in the space, and that is essentially with the addition of the Coanda wing option. And we can even integrate lighting into it, which is shown in the top right there. So you can integrate services in there if you have a pretty tight ceiling space and the lights are already running parallel to the chill beams. We can look at integrating those into it, which is a nice option. I'm going to show you a smoke video from our tech center in Suwanee. Here's a exposed application showing the smoke of a typical linear without the Coanda wings installed. And you can see it's throwing pretty much directly downwards at about a 45 degree into the space. But what we're going to do is show you with the Coanda wing on the right there, how that wing essentially allows it to hug that surface just long enough to get the trajectory going horizontal. And that way you don't have any dumping or at peak load, throwing the air directly down into the occupied space. This alleviates any discomfort or opportunity for draft and discomfort. So in terms of labs, this is again a local project that we did at Novartis, and you can see the beams installed above the see the flow hoods here, the benches and workstations. Again, usually have lighting directly over top the benches. So we've got the beam closely coupled right next to the lights, which is a good option there. So next up is the chill beams in a hospital that we wanted to show. So on the left is a standard ACBL for just a normal patient-style acute care space, and on the right we have, in most hospitals there's a psychiatric or a behavioral wing typically, and so we've got our security beam installed up in the ceiling, and you can see even the hard lid style of ceiling. But the fasteners here are tamper-proof. Sorry about that. Tamper-proof, and they require a special tool to remove the face and get access to the coil. You can also notice that the perf spacing is a lot tighter on that, and that is by design. That's to meet various local codes and even Title 24, Code 24 on the perf spacing, and even that down to the diameter of it. For various reasons and protecting the patients themselves. But there's also, some of you might be able to see there's a perf even up within the slot diffuser to keep anybody from being able to get up there and mess with that or run string through it, essentially to provide the maximal security within the unit. Next up is the passive beam installation. You can see these along, you can see my cursor, passive beams installed up against or close to the wall, and you can essentially couple these directly up against each other in line. You don't need to space them necessarily apart. You can run them continuously. Just important to have space around the sides and above the passive beam itself so that air can get up behind it effectively. So here you can see it directly above a sort of a higher load generation area near the printers and the large equipment. So all of that is going to just naturally rise up, get up above the coil and cool off, and then those passive beams will provide the cooling to the space through them. Now you always need a ventilation component to it, obviously. So again, because we're not providing fresh air to the beams in the case of the passive unit, so here we have the ceiling ductwork connected to the louver grills, just right off of that ductwork, supplying the ventilation latent airflow requirement to the space. So lastly, we have Marston Hall in Iowa. We wanted to mention this one. It's another LEED Gold project, and they were operating at about 53 kBTUs per square foot per year. And they achieved just over 33% savings over the baseline. Again, you're seeing a trend of roughly 30 to 35% savings over baseline, and that it realized about $40,000 of savings per year, and pretty close to the initial energy model predictions. All right, so again, just a quick reminder, if you have any questions, do please enter that into the chat in your panel, and we'll make sure that we're answering those, or maybe even during the presentation we see those come in, we can talk to them as required. So again, thank you for your time. I'm now going to pass it over to Ed Fruth to talk about some history of chill beams.
Well, good morning, everyone. If you enjoyed the last 30 minutes of presentation from Chris, I'm going to do a little bit of history of chill beams. It's not a long history. The history of chilled beams is really only about maybe 70 years, but in reality, it's here in the United States, really less than 20. But since I'm the old guy in the room, I was elected to do this. So let's get into it. Again, I'm the regional sales manager for the Northeast. I've got roughly 42 years in the business, with about 10 years in chilled beams. And that 10 years in chilled beams is right up there. There's only a few people in the United States that have that kind of time in chilled beams alone. So where did chilled beams begin? As far back as we can see, the introduction of the technology, which would really be the induction process, goes back to somewhere in the, we'll call it the early 1800s, where they were using this process to really increase fire, the intensity of fire. And then from there, we go all the way into the early 1900s, where once again, scientists were using the induction process for more heating principles, melting metals, and foundries and such. So the process itself of induction, Chris did get into, but this is pretty much the technology, is that you push air through a small orifice, the velocity increases. Once the velocity increases, that creates a negative pressure over whatever source we have. And in this case, it would be the coil in our beam. That negative pressure induces air from the space into that increased velocity air, if you will, and then that's pushed down to the space. So this is used in many, many different applications, not just HVAC. But the interesting piece of it, from my perspective, is that it's free. That velocity and induction process doesn't require any motors to pull that air in from the space. So that's kind of our primary way of saving money. The beam has no any motors in it, any mechanical pieces. That nozzle is the whole process. We do have a little power, if you will, and that power would be the air that comes from the air handling unit. And that air is really our engine as it's pushed through that nozzle. So once again, the induction process is really the history, if you will, of chilled beams, but we can get into it a little bit further. So the first HVAC device that we can find is the induction unit. And the induction unit was created by Willis Carrier. Roughly 1937 is when that device was created. And the first installation was roughly 1940 in Portland, Oregon, in a United Nations building. Sadly enough, World War II really stopped the process, or the progress, I should say, of the induction unit itself. HVAC systems, or really anything that was a heavy metal user technology, was really kind of put to the side. All of the metals at that point were used for the war. So it really wasn't until after World War II where we begin to see induction units really coming in vogue. In really 1950s is really when the induction unit really started taking place. And that was really because of the introduction of really high-rise buildings. So most of the guys that are on the line right now are, Bostonians or are from New England. And, a few of the first buildings in the New England area, or even Boston, that had induction units were buildings that were built in the late 50s, early 60s. That would be the Prudential Center, State Street Bank, 225 Franklin Street. These were, high-rise buildings, roughly, in the 30-story plus scenario. And one of the pictures or the diagrams that's shown on this slide shows a riser going up the building, and then there's 2 induction units that are served by that riser. That riser is the primary air. So ideally in these high-rise buildings, there was quite a bit of duct work, if you will, to these floors. And once you got to the floor, the induction unit itself um, was a pretty simple process. Induction units, as compared to a chill beam, is kind of the upside down process, where a chill beam really kind of blows um, down, if you will, into the space. The induction unit is set up so that it blows up against the window. And although the diagram here is kind of, a little generic, if you could see where it shows the primary air inlet going in, there's a series of nozzles that are there. That process pulls air from the floor across that coil, then up the top of that air outlet. So once again, it's that increased velocity that pulls the air or induces the air from the floor, or in the beam scenario from the space. But the induction units themselves were really kind of primitive in the form of some of the issues that came. One, it had pretty high pressure. The primary air going to an induction unit was really anywhere from 1.5 inches of static plus. And when you walked into a room that had an induction unit, you knew that there was some air blowing. There was quite a bit of noise associated to them. And they were they were a wet device. So not only did we have condensation issues in the pan, excuse me, in the condensate pans that were associated to them, but also the drains that came off of these pans were very typical to clog and plug and create all kinds of other issues. So although it was a great technology and is still used today with a little more refined, if you will, uses of the nozzle in the air that eliminate some of these issues. You know, the induction unit was a kind of the first introduction to chill beams here in the United States. So if we really start looking at other kind of technologies, if you will, really the first chill beam that we can see that hit the United States was roughly in 1986 with a passive beam, or I should say in Europe, which was Stockholm, Sweden. And the passive beam, as Chris had shown, really is a very simple device. It's just a coil that they mount, above the ceiling, and as the warm air rises, it finds this cold surface, which is the coil. The air around that coil changes its buoyancy because of that warm air cooling off. And once the warm air cools off, it gets heavy and it falls through that coil into the space. So, passive beams are a really first line introduction to really chill beams. And 1986 is really the beginning of them. So once again, rises to the ceiling, finds that cold surface. The buoyancy changes because the warm air changes to cool air, and then it falls to the floor. From there, basically, for North America, 2003. In 2003, the first installation of chill beams was installed here in Waltham, Massachusetts, at a company called AstraZeneca. I've been to the facility multiple times, and as early as, or I should say as late as 2018, Talking to their facilities people, they have still not had to provide any maintenance to the beams that are part of that facility. So it's a testament to the simplicity of beam construction, and used in the right applications, chilled beams really provide a very long life cycle. After 2003, we had about, I would say, 5 or 6 years of really good growth. And most of that growth that happened after 2003, once again, was here in the Northeast. Facilities such as Harvard Business School, Wellesley College, Yale University, all of the big major institutions were looking at chill beams at this time and installing them. Around 2008, 2009, the economy kind of took a hit, and with that, chill beams stalled again. I should say stalled in their process of being a traditional HVAC product. And it really wasn't until roughly 2014, 2015 when the kind of the economy came back into vogue that chill beams started taking off. So today, in most of the large metropolitan cities, specifically with customers that are building owned, if you will, and someone that is not looking at a first cost type scenario, is looking at a very efficient building. Chill beams is really the choice for building systems. We're finding that with the change in energy codes that are happening, specifically things like the stretch code here in Massachusetts and the requirement for dedicated outside air systems, that chill beams is really one of the best ways to get a very efficient building and to meet the energy code. So we see chill beams in the future as really a best practice design for meeting the energy code. And moving forward, there's some new technologies that are coming up that integrate other systems into the beam, things like lighting and other really pathways, including some clean air type applications. So that's roughly the history. In short, here in North America, really, we've seen chill beams from roughly 2003 with their first installation in AstraZeneca to where we are today, where still New England is really the largest user of chill beams in the United States. The East Coast in general is really where the epicenter of chill beams really are. It is used in other parts of the country, but in this area is really the most usage. So that's our history. And any questions with that? If you have them, please type them in to the chat side of it, and we'll do our best to answer that. If there are no questions, I'm going to pass this on to Nathan, and we're going to dive a little bit deeper into chill beams. Nathan?
All right, thanks, Ed. Let's do a quick audio check. Is that coming through? And we'll get started. At this point, now we're going to jump into the software. I'm going to back out of PowerPoint for a while, and we'll do a deep dive into some tools that we have that can help you guys design. So if you're in the early stage of designing a system with or without chilled beams, if you want to consider the chilled beam system, this is a great tool to use. Real quick before I jump into this, I think we have a question. So the question is, will we talk about the relative humidity on the air handler? And absolutely, that's going to be a huge topic this afternoon. So I'll hit some of that in this section, and we'll have a big discussion about relative humidities and air handler selections, later today after lunch. But while I'm here, I'll actually hit some of that in a second, talking about the software as well. So before we jump right into this, this is a software that is available online, so feel free to take a look at our website, priceindustries.com/beams, and you'll be able to find the software online. So that's one way you can follow along if you want to take a peek at this. I also have a PDF that has been uploaded to GoToWebinar, so you can see that and take a look at that. And then after we do a tour of the software, we'll jump into a quick layout exercise and walk through the whole process of where do you start sizing a chill beam, picking the model type, and how you get it basically from the idea over to actually laying it out to a floor plan. So we'll go through all those steps here, and we'll actually back up into this, and I will do a quick download of our fresh software. So priceindustries.com/beams. We'll take you to our website. You can find our software under the resources drop-down menu. And it is an Excel-based tool. It is based out of Microsoft. It will not work for iOS currently. So one thing to note is you need a Windows-based device to use this, but it is Excel. So everybody with a Windows computer and Microsoft Office should be able to access this and to use it. All right, so let's open this download. And we can walk you through the entire process from a fresh copy. There's going to be a couple questions right at the beginning once it opens up. And we got to make sure to enable macros, otherwise it will not work. There we go. So I'm going to zoom out a little bit so you guys can follow here. But a quick point to make on the first page of this, you will need to enable the editing. Let the macros work, otherwise the back end of the software will not function. So that's the first step to take, is to enable the editing here. Enable content. And this first page is the input wizard. So if you know some characteristics you want to use for your beams, any kind of zone naming, area of the zones you're looking into, answer a couple questions here. If you click update, it does not actually update. You'll need to go back to the website to re-download the most current copy. So that's a quick point there. But this is the input wizard. So essentially, if you have some information you are aware of already, you can input these parameters in this page and then push that back into the software. If you are experienced with chill beams and you know what you're looking for, you already have an idea of what sizes you want to use, you can open up this advanced inputs button, and that'll give you some more columns to fill out. So if you want a 2-pipe or 4-pipe system, you have some links in mind, you already know some of your flow rates and your inlet sizes, you can fill out any of these points, and that will take you, it'll carry all that data through back to the performance page. So we'll jump into that performance page now. But if you are aware of anything, you can copy and paste it here and push that in. But before you start actually selecting anything, you will need to hit this Go to Performance button, and that'll take you to the main page where we can actually start doing some work and fine-tuning the chill beam you want to size. So one quick note about the spreadsheet is we can do up to 300 lines at a time. It will slow down as you add more and more lines. It should take no less than 5 minutes to do a selection, but typically it's much faster than that even. But you can do anywhere up to 300 zones. So now we are in the main page. This is the page we'll spend the most time on, and walking through how to select different chilled beams, and a couple features that will make your life a little bit easier if you are going around selecting these. But before we dive into the individual selections, let's do a quick tour of where everything is at. This can be an overwhelming software. There is a lot of information here, both that you can input and also outputs that you cannot change. So on that note, the green cells here, all these base cells are going to be inputs, and all of the white cells are going to be outputs. So these are cells that you cannot modify. All the green cells you can modify, but you do not need to actually touch every single one. The program will do make some assumptions for you, just to make your life a little bit easier, but you can always go back and change those items and fine tune this as much detail as you would like. So starting on the left side of the software over here, we have a title block essentially for your project name. You can add a revision level in as you save these selections. Also, the date is current. Below that, we actually have the room conditions. So this is going to be the conditions you want to keep in your space, and we default to 75 and 50%. So you can modify that if you wanted a more humid space condition or less or drier. But we find that 75 degrees dry bulb and 50% humidity is kind of a good starting point. And we see most designs starting here. So we'll talk a little bit more about what that means to moisture content in the next after lunch, the first presentation after lunch. But for now, we'll leave it here at 75 and 50%. Also, you do have an on-coil temperature. So if you wanted to look at what the temperature is actually going to be at the coil, so you know there's a 2-degree thermocline from the floor to the ceiling. Maybe you have a very high installation for the chill beam. Maybe it's a 20-foot ceiling or so. That could see a higher temperature than what would be at the floor. So you could increase this a couple of degrees. If I had a 2-degree delta there, I would go to 77. So that is another option. I'm going to leave it at 75 for these selections, assuming there is no thermocline in the space. Then next we do have a noise target. This is essentially going to be the max noise allowable on the selections, and that's going to tailor what the software is going to do when you run the auto select, and it's not going to go above that NC level. So you can change that. You can go up or down. Say you have a large open warehouse, maybe you don't care about noise so much. You can bump that up and get more energy density per lineal footage of beam. But maybe you're in a studio and you want a really quiet space, and you can drive it down to 25, 20 NCs, and it's going to keep a very quiet space condition. Now, in my experience on the noise side, 35 NC is a pretty good target. We find that that's pretty much a good office level of noise. Much lower than that, it actually gets uncomfortably quiet, and many applications, like Chris mentioned earlier, will actually add a white noise screen back into the building. Sometimes it's too quiet, and you actually have to have some noise produced to essentially as a privacy screen in the building, so you can't overhear every conversation around you, causing some distraction in the space. So that is one thing with beams. It's a very quiet system, so keep that in mind as you select these. They may be too quiet. And then other places like a sound studio where it really does matter, you can also check those levels and NCs out as well. In those cases, you would actually want a very quiet space. So a couple of notes there. Also, we have a room attenuation field. So if you have a lot of carpets or drapes or anything that's going to absorb some noise in the space, you can change this. We'll start at 10 decibels of attenuation. If you have a lot of concrete, hard walls, a lot of sound reflective materials in the space, you can drop that to 0 and assume no attenuation. So that is another parameter that we can change up here in the front end. And then moving along from there, these are all the room conditions that you're going to see in the space, so outside of the beam itself. Next category we have here is the primary air conditions. So this is essentially what the air handler is going to be feeding to the chill beam. And again, we make some assumptions for you, but these green cells you can change. So for example, if you have a more typical air handler selection for a VAV system, a more typical selection on the wet bulb side of things, you might be at 95% humidity and an almost saturated design there at 55 dry bulb, 54 wet bulb. With beams, and I will go into more detail on this thought process in a little while. We typically start at a little bit drier of an air condition, and this is really to maintain your space moisture content and keep that dew point exactly where you want it to be. Otherwise, you may lose control of your dew point, and then you have to bump your water temperatures up, and you end up losing some capacity, which we'll go into some more detail on that in a little while. So for most of these selections, I'm going to start at 55 degrees dry bulb and 51.6 degrees in the wet bulb. And there is some logic behind this baseline, but one thing that's important now is that this is a 49-degree dew point off of your air handler. So that's where we're going to start at. You can adjust these, and it will affect your whole selection. So if you do have a more moist entering air condition, you actually will not get the same latent load per CFM. So we'll show what that means in a minute here as well. And then below that, the next input in this section is the max airside pressure drop. So if you have a max allowable pressure you can keep in your ductworks, maybe you're at the end of a duct run and or have a very long duct run and you can't get to that 0.75 or 0.8 inches of static, you can drop that down to 0.5 or anything above 0.2 inches of static. 0.2 to 0.8 inches of static is a typical operating range for chill beams. But also for the sake of this presentation, I'm going to leave it at 0.75 as a max. So that's giving me a threshold where it's going to flag anything that's higher than that. And if I run the auto select, it will not select beams over that level. Yeah, so I think we have one question.
Not necessarily a question.
A side point.
So a side point regarding the static pressure on the beams when you're putting it in here. You know, static pressure is kind of directly related to noise. So these 2 points that Nathan is bringing up regarding your NC levels and then kind of picking level goes is not linear because it really depends upon the length of the beam and the size of the inlet. So don't get fixated on the static pressure piece because it really depends on a lot of other components. This is just a starting point. Nathan mentioned 2 other numbers. You know, don't go below 0.2. And the 0.2 piece becomes a function of our ability to induce air through the nozzle. So going back to the kind of basics here, the velocity as it goes through the nozzle is really the power we need to induce air from the space. When you drop below 0.2, it's roughly 1,200 feet per minute at the nozzle. That 1,200 feet at the nozzle is a point where we can't really accurately measure the induction rate. So good rule of thumb is don't go below 0.2 because we really can't be too accurate there. Good rule of thumb, I wouldn't go any higher than the 0.75 unless you're making an individual selection. And then once you make your selections, you may want to consider dropping your static pressure levels down, looking at the overall selections that you have to try to make your selections that much more accurate or robust. So again, don't get caught up in that static pressure piece. Pick a number to start with, and then dial it in as we start making our selections.
Yeah, great point, Ed. And we typically just have a range of static pressures, 0.2 to 0.8. Just kind of recap what Ed was saying there. The threshold on the bottom side is to make sure that we know what's induced through our water coil. And on the upper end there is what your system can actually produce, and also what's going to be dictated by your noise levels. So we'll go through some selections and show the effects of that as well. Those are all great points. So that's the last thing on the air side is the static pressure target range, the max upper limit there. Moving on below that section, we also have the entering water conditions. So this is where the beams are a little bit different from a fan coil system or other hydronic systems that you may be more familiar with. Generally, we're going to start at 2 to 3 degrees above your space dew point, which if I scroll back up real quick at 75 degrees and 50% humidity, we're going to be at 55.2 degrees as your dew point. So we want to say 2 to 3 degrees above that. 57 is a great starting point, 58. We even see up to 60 at times. You don't always need to go that high. If you have an operable window or a doorway that goes to the outside, that might be a space where you want to consider having a higher entering water temperature. But in most spaces, 57, 58 is going to be a great starting point. It's not going to be the same as a fan coil system, which is much lower. So that is a point you want to make sure your facilities team understands, and they don't come in after you design the system and commission and drop that water temperature down below the space dew point. And we'll hit that a few times today, but that's definitely something you want to understand about this system. And in heating, anywhere from 90 to 140 or so is pretty common. 110 to 120 degrees, I would say, is the most common. We do have some options for different mediums. So if you have a northern climate, such as Boston, or if you're up in Canada, wherever your project may be, we can add some glycol into the mixes. And you can pick a glycol, ethylene or propylene, and then you can fill out a percentage here. So for example, if you wanted to start with 25%, you can select that, and there's a range of percentages you can enter here. And that's both for the heating and the cooling loops. You can add different levels of mixes for each loop. So that's one thing to consider. For these selections, I'm going to just start with water, and we'll leave that a little more simple, and I'm not worried about the glycol percentage here. Then below that, we have the max waterside pressure drop. We generally just leave that at 10 foot of head. That's going to be the max allowable pressure drop. It's not going to select anything higher than that. If you want to make that smaller or larger, you can do that, but 10 is kind of our baseline here as well. And then we have the last item here on the left side, these global parameters. It's going to be the stratification credit. So this is essentially derating your loads, or for a stratified space condition, if you're using that floor-mounted chilled beam that Chris showed earlier, the ACBC, that's going to be a displacement style unit. So the space condition is going to be stratified, and you would have a derate essentially from the loads that beam is going to see, because some of those loads would be exhausted or not seen in the space occupied zone. So that's also a feature you'll see just for the ACBC, will not apply to the rest of the fully mixed products. So with that, that's the global parameters. These are going to apply to every single line in this software. So essentially, each of these lines is going to be one zone, and you can zone this however you want to. If you're doing a narrative level or a higher beginning phase conversation, you may want to use a zone per floor of the building. And then as you get into the project, and you can fine tune your resolution of how many zones you have, what details, how as you get more and more detailed in your design, you can break that up further and spread this out. But even for a very entry level or beginning conversation level topic, you could just start with a zone as a whole building and run your trace trade loads in the entire building and kind of take a peek at, what's your total occupancy, what's the total square footage of the project, and from the occupancy you can get a quick latent load estimation, and from the square footage you can say maybe the building is going to see 25 to 35 BTUs per square foot, and pick one of those and get a total sensible load for the building. So I'll walk through that in a little bit. We'll do a quick narrative level discussion or a budgeting discussion, and how I would start this conversation from that level. Once we finish this tour, we'll get into that. So this first section here, now we've finished the global conditions on the left side. This is going to be our wish list for the space conditions. So this is what we want to actually see in each zone. So for examples, say that we are looking at a very small zone now. We've actually got a small office space. You may see 5,000 BTUs of sensible load. We do break out the latent load. We're not often going to talk about a total load. We do want to separate these and consider them separately, and not do a total capacity selection like we would with a condensing unit. So that's where beams are a little bit different. We designed the CFM, the air side, based on the latent load to make sure we have control of that space dew point. And the sensible load is actually a separate parameter, which is just going to be handled by the water side mostly. There's still some sensible capacity of the air side as well. So 5,000 BTUs of sensible, and let's say we just have 1,000 BTUs of latent as an example. And we could add heating in as well. Go back to 5,000, have the same as the cooling load. And from there, this is my wish list for this space. I'm assuming one beam at this point. The software may help me figure that out in a little bit. One rule of thumb, I'm not sure that we mentioned earlier today already, is that you can expect about 1,000 BTUs per lineal foot of chilled beam, of active chilled beam. Passives are a little bit lower, around 350 to 400 BTUs per lineal foot, essentially a third of the capacity of many active chill beams. And I'll repeat that a few times today as well. But so for example, if I'm going to start a design, I see 5,000 BTUs in this first zone. I know that rule of thumb of 1,000 BTUs per lineal foot of chilled beam, active chilled beam. So I can expect at least a 5-foot chilled beam in this case. And that 1,000 BTUs per lineal foot is a fairly conservative number. So I could probably get away with a 4-foot chilled beam in the selection and make it work. And we'll see what happens when I actually start selecting these. Right now, nothing is showing up. I've just put in my wish list items. There is no beam selected at this point. So once I select the model, it actually will start filling in some of this data. So before we do that, if you forget which models we have or you want to see what we call them, there is a button up here in the top for beam types. If you click that guy, you'll see a few different models. These are all of our models with pictures and our names. So if you don't remember the name of which one we call which, You can go back and verify with a picture. And this is also a hyperlink. So if you do click it, it will take you to the website where our submittals are located and some other literature and catalog information. So you can go straight to that with this link here. We're not going to do that today. We're going to go right into a selection. I'm going to start with the ACBL. This is the unit that we see sent out the most. So we'll do most of our selections around this unit. And I'll do a couple with the ACBR later as well. So closing this, getting back into the software, I've decided I'm going to use the ACBL. So we'll use the two-way discharge variant. There's two options there. Same with a 12-inch wide version of this product. So we'll start with the 24-inch wide with a two-way discharge. And right away, you see I've got some red here, which is generally not a good thing. In this case, I'm not worried about it yet because I've not done any selections. I've not tried to fix it. If you put too much airflow or you run out of airflow for that zone, that can show up as a problem, but it will notify you you're not meeting the conditions you're asking for over here on the left. So for example, I want 5,000 BTUs of sensible load. 1 second, we got to plug this computer in. So we'll keep going and I get that plugged in. But I'm at 800 BTU short on the sensible load of this chilled beam. I'm actually fairly short on the latent load as well. And then for the airflow, for this latent load at these entering air conditions, the 55 to 80%, I'm going to need 109 CFM, but my default selection was starting at 50. So I'm about half of what I need on the CFM. So this is your total outputs per zone. So if you have multiple beams, this is going to sum all of the conditions you've got, and it'll take into account every single beam in that space. So if you have a zone of one beam, that's going to be showing one beam. If I have two beams in the zone, it'll show me the capacities for two beams. So we'll do a quick example there. So now you can see I've doubled my sensible load by adding another quantity of beam. We'll go back to 1 for the selection. And if you delete it, it will actually think for you how many beams do you need. So we're defaulting in a 4-foot chilled beam. So I'm still not meeting these loads. What I'm going to do first is I'm going to max out the water side. So these are my total zone outputs. I'm going to go farther to the right. And these are my individual beam parameters. So this is what I want to change to make sure I can satisfy these space conditions. First thing I'm going to start with, I don't want to add more length to the beam. That's going to add some cost. I want to do this as cheaply and effective as possible and not have too much chilled beam. So what I'm going to do is I'm going to start with the water side. I'm going to bump that up to 2.5, which is the max GPM, the flow rate that we kind of stop at. We do go up to 3 every now and then, but we find past 2.5 GPMs, you don't really see a whole lot of capacity, and you got to push a lot more pressure and a lot more flow through the chill beam, but you really don't get a whole lot of BTUs back from that exercise. So 2.5 is kind of where we typically stop. You can go higher if you need to, but that's at that point I would start adding air back to the space. So you can see here on the left side, back in that total outputs, I was at 4,200 before. By adding 1 GPM, we started at 1.5. Now we're at 2.5 GPMs. We've added 200 BTUs. So it's not getting me quite all the way there. It is a little bit better. So we'll max that out. But now that did not satisfy my cooling conditions, I got to add some CFM. So right now we're at 50 CFM per chilled beam. Let's go up 5 CFM, and you'll see the effect. We just had 1 GPM and got 200 BTUs. If I had 5 CFM, let's see what that happens. What happens there? So I actually switched nozzles and went a little bit lower actually. So kind of a surprise there. So you'll notice I have a 35 nozzle. As these nozzles increase in size, you actually change the induction ratio of that chilled beam. So I went from a 35 nozzle to a 40 nozzle and actually lost some induction. And that's why the performance went down, which may be counterintuitive. So at some point we flipped the nozzles because my max pressure was at 0.75. I had to increase the nozzle size to accommodate that extra airflow. So we're at 50, but now we'll start to see a big increase. Add 5 more. We're up 300 BTUs by adding 10 CFM essentially from the original selection. Not quite there. Let's add 5 more CFM. Did not do a whole lot. And we'll keep bumping that up until we get to the 5,000. So I added 20 CFM and I got 800 BTUs out of 20 CFM. So that had a much larger impact than adding 1 GPM on the water side. And the reason you'll see a larger swing in capacities on adding some airflow to the beam is because the induction ratio magnifies the effect of every CFM. So in this chilled beam, there is a way to see the induction ratio. We have it right here, it's 3.3. So that means for every CFM that I add to this chilled beam, I induce 3.3 CFM through the water coil. So we're getting a lot of air movement in space by adding just a little bit. So I added 20 CFM to the primary air of the chilled beam. I'm actually inducing about 60 CFM more than I had originally. So that's giving you a lot of capacity out of the water coil, and really playing off the GPMs that we added, and making that water coil more efficient, or having a larger capacity. So that's why you'll see a larger swing on the air side. Changing the GPM may not have a huge effect, but it will have a smaller effect and have some effect. So we like to max the water side out first, just to stay as efficient as possible. You really want to use the water system for as much of the load as you can get away with, and lean on that and try to reduce your fan energy. That is the main goal of chill beams, to stay energy efficient. So that's why we'll sacrifice the water first and add some more pump energy, and then bump the air side up as we need to. So the next thing you'll notice, we did satisfy the sensible load. We're good, 5,008 BTUs. So I'm happy with that selection. The red went away. The next selection we got to meet is the latent load, and we have two options here. Obviously, the first is we can add more airflow to make sure we have more dry air coming in. A little bit more expensive of an option could be to take a look at our air handler. And maybe we're stuck at this volume of airflow, but we don't really have the ductwork size to go any higher than we have. What's our other option? And it's really just drying out your entering airflow from the air handler. So if we have 55 and 80%, that's our default conditions here. Maybe I'm able to drop this 51.6 leaving wet bulb down just a little bit, and let's say maybe 75% relative humidity from the air handler. So in that case, you're going to see this latent load start to go up. So just because I didn't note it before, let's go back to 80. And at 80% humidity and 55 dry bulb conditions from your leaving air temperatures on the air handler, you're at 644 BTUs of latent conditioning. If I drop this 70 to 75% humidity down from a 51.6 to a 50.8 wet bulb, I actually get about 150 BTUs of latent capacity. So that's another way to look at it. If you have a very latent driven space, you may want to dry this air out as much as is economically viable for your system and your budget. So that's one thing to consider, and we'll talk about this in the future, but that is one thing we really like to look at first. I'm not saying you have to go down to a 45-degree dew point. That may not be achievable, but this is something to look at. Make sure you're not supplying saturated airflow, because in that case, the latent condition is going to drive your airflow up, and we really want to keep that airflow down as low as we can get away with. And there's going to be a variation of what you see and what you can get away with in your project. In this case, I would add more airflow. I'm seeing 70 CFM. I'm seeing in this side, I needed 109. If we had dropped this back to 70% humidity, this number will update and show you how much you need. So I'm only 3 CFM short at this point. And the red went away actually on this because I'm within 5%. We give a 5% tolerance to make sure we're close enough. We're only 50 BTUs short, so we're probably going to be close. And this is a worst case condition, so it may only be an issue a couple times a year. So that's why we give a 5% buffer, but that is one thing to check. The red's going to go away because we're within 5%. But let's go back to the 80%. Maybe the rest of the zones are fine. I have an example to walk through that scenario in a few minutes here. But what I would do in this case typically is if all the other zones are meeting their latent loads, I would go back and just add some airflow to this space. So I know on this side I have one beam. I'm asking for, or the software is telling me I need 109 CFM. So let's just go ahead and put 110 in this CFM. Because I have one beam, if I had 2 beams, I would divide that by 2 and give each beam 55 CFM. So side note there. So now I've met all my conditions. My sensible is good. I'm 1,000 BTUs over. So I see that that's too high. I'm actually going to go back and I'm going to drop that GPM. So because the latent drove my CFM requirements up, I'm overcooling the space at this point. So I'm going to go back and drop a GPM out of there. Let's see how close we are. We're pretty far over, 0.5 GPM. Let's lose another GPM. I'm pretty close. I actually dropped a little bit below 5,000. So I'm going to add a little bit of GPM back, 0.6 GPM. And now I'm over 5,000. We're good to go. So this is essentially the process of fine tuning this selection. This is how I would go around each individual beam. But let's say I have a few more beams and I don't want to go through that whole process every single time. It is pretty time consuming, and before we had this Excel tool, we actually used to run each of these selections by hand. So I'm going to run a few more here, and we'll show you what the software can actually do for you. So I've added a couple zones in. We got zone 1, 2, and 3. I'm not meeting my conditions. I do have to add a model in before it's going to select anything. It's not liking my default selections here. So instead of going back to that same process we just did, I'm actually just going to hit this auto select button. So if you don't want to go through and tinker with every single beam, you can absolutely start here, run an auto select. Now it's already done all of that thinking for me. It did exactly what the process I just went through, but did it much faster than I can do on my own. So this is a great tool to use if you want to do a quick selection. If you are still not exactly happy, maybe you don't like the CFM that's provided, you can go back through and try to fine tune it a little bit and go and change each individual line. But this is typically how I'd recommend starting these selections. Is just run an auto select. It'll make your life much easier. If one doesn't make sense, you can go back through and run the individual room auto select. So you don't need to run every single beam, every single zone, every single time you select. So you have multiple, maybe 100 zones. You may not want to go back and change. You made some changes. You don't want to lose those changes by running the auto select on every single zone. So the individual room zone is a good way to do that. Go back individually and change it. And maybe in these 2 zones, I'm happy with the selection. I got a quantity of 1. Maybe this zone I'm expecting more. So what I can do, as long as I've selected 1 cell in this row, I can go back and individually auto select. Maybe in this case, I don't want to optimize for quantity. I want less airflow in this zone. I can optimize for the primary air. You also can toggle these adjust quantity, adjust length, and you can allow it to either change your quantities or not. And you can also pick return only even links. If you have a ceiling grid that's 2x2, 2x4, you can just lean on just even links. So those are some options as well. I'm going to allow it to, I'm going to check both these boxes and allow it to adjust both quantity and length for this exercise. And we're just doing this one line, the third line. I've got a solution, and it's basically the same thing in this scenario. But so we have a pretty accurate selection already. So let's go back and try this again and see if I can get that CFM a little bit lower. So maybe in this case, I'm at 500 CFM, but maybe by air handler, it's a retrofit, and I've got an air handler size for 400. So let's see what we can do. Can we get some more airflow out of that system? So we're going to optimize for the primary air. And it looks like no, we were actually pretty close on these already. We added some beams, so we really are at 495 CFM is still. We've not gotten any CFM out, but sometimes you'll see a very different selection between the optimizing for quantity and optimizing for primary airflow. So in this case, it looks like 495 is the number we're going to hit for these 3 beams selected. So going farther to the right, that's a quick way to use these green cells. Once you've done your selections, if you want to go even deeper into each individual beam and what it's seeing, on the far right side here, we do have our active air side data, and even farther right from that, we have our water side data. So this is pretty much everything you would ever want to know about these chilled beams. And these things do come up every now and then. You don't need to schedule every single item in here. What we do want to see on the schedule is at least your sensible load and your latent load and your heating loads for your total beam. So in this case, these 3 items are just for my air side. Over here in the water side, you're going to get your total sensible heating over here. Those are going to be the ones we want to see. And then we also want to see the latent loads broken out, which would just be in the air side in this page. So this is coming from your air side. And also here's your air side heating. Typically in most selections, we're actually going to be providing 55 entering air temperatures year round, which means that in heating, you're hurting your heating performance by providing that colder air. You can do reheat, VAV upstream reheats and provide warmer air. That's totally an option. And we see that pretty often in more southern climates where they don't need the same heating loads. They don't want to use the water to heat. They'll use an electric heater in the upstream VAV, heat the air that way. So that's another option. But this does take into account the loss if you have 55-degree airflow coming into the beam, even though the hot water coil is running as well. And this takes that into account. That's why in the heating side, you'll see the total coil BTUs just from the water coil, 7,500 here. We're actually lower. We're subtracting this number out for the air side, and that's going to be our total sensible. So that's the variable we want to see and we want to schedule. We don't care so much for the individual coil performance. What we want to see is the impact of the chill beam on the space and not the individual components of the beam. This is the more important item to schedule, in my opinion. Then lastly, here we got your living air temps 95 and a little bit high. We like to be within 15 degrees of your set point, so 90 is usually a cutoff. But we do see higher pretty often with no major issues, but that's one thing to keep in mind. You don't want to stratify that hot air if you're mounted from the ceiling. And it's also the 25 degree delta T on the heating side, and on the cooling side, we have a lower 9 degree delta T, which is actually in the higher range for the cooling side. So that is all the parameters. There's a bunch of information here. One other thing I like to point out in this slide is we do have a transfer effectiveness. So this is kind of a metric you can use to determine is this chill beam selection efficient or not. So these are decent. We actually can see much higher. If I use a smaller nozzle size, you'll see that number go up most likely. So for example, if I came back over here, I'm going to adjust the target pressure. You can see there's the target pressure. There's also an exact pressure. Exact pressure is what I'm actually seeing at the beam, and target is the max allowable for that individual beam. So let's bump this middle one up to 1 inch of static. Kind of on the high end, you can see right away, it doesn't love my 0.95 I'm seeing here. That's because my threshold on the left side, the global parameter, is a 0.75. And it also doesn't like my noise. So that's usually where we see the issues come in. On the air side is if you have too high of a static pressure, either you can't get it to the beam at that level, there's too much leakage or obstruction in the ductwork, and you need to ramp your total static on the system to get all the way to the end, get that 1 inch of static all the way to the end of the duct run. Or you see a lot of noise out of the beam. In this case, my highest decibel on that decibel curve, octave band, 8 octave band curve, it's going to be 46, and I'm at a 31 in C. So I had selected a noise criteria of 28. I'm going to bump that back to 35 because 31 is not too bad for most office selections. But one thing you did see is we should see this transfer effectiveness go up. So let's try going a little higher even. See if we can get that up as high as possible. So it's not liking it because I don't have a lot of GPM. As I add some flow rate to that water coil, you're going to see more capacity. Your transfer effectiveness is your BTUs per CFM, so it's how much energy am I getting out of every single CFM. And to give you a baseline, for a VAV system, you're going to see about 20 to 21 BTUs per CFM. So in that case, I'm 3 times more efficient per CFM. I have 3 times as much capacity per CFM as I do in this line as I would have with a VAV system. And these are about 2.5 times. So not bad. Anywhere from, I would say 40 plus is a pretty good selection. 50 is pretty common. And I've seen all the way up to 100, 110 on that metric. So that's a good way to kind of see, is my chill beam doing more work than I would have from in the 20s, even down maybe below 30. You're probably going to have an expensive diffuser, and it's not worth it in that space to use the chilled beams. You can have a much cheaper option if you need that much airflow, because you're not using the water side as much as you could. So that's one metric to just make sure you have a good selection. And past that, once you're happy with the selection, maybe all these items I'm happy with, I don't want to change anything, ready to schedule or go push this out for a bid, I can run a performance schedule. It's going to ask me to check all the links, make sure everything is okay, my inlets as well. And now it's taking me to a schedule page. So this is what you can use to get all of your performance characteristics out there and send this for others to bid. And we have some toggle switches up here at the top, radio buttons, and you can check these boxes and add different characteristics into the schedule page. So maybe you don't want to include all the coil capacities, you just want to show that tensile or the total capacity, or maybe you do want to include the coils separately as well. So you can turn those on and off. There's a pretty nifty button here as well to print the PDF, which I enjoy using that feature. And also, if you do have a sales rep you're talking to, you can export these all in line strings. The rep can take this software and pull it right into our sales catalog software. So that's a pretty easy way to talk between those. And it'll make sure you keep all of your nozzle sizes, all of your different parameters in those selections. And it's not going to drop anything. So it's an easy way to get a quick budget costing by using this spreadsheet. So now we're going to go back. We're not going to spend a ton of time on this page. We're going to go back to our selections page. And what I actually want to show you from here is the building summary. So I mentioned the transfer effectiveness is one way to kind of judge if I have a good selection. I would say anything above 30 or 40 is pretty good. The higher, obviously, the better. But let's look at another way to check that out. And what we're going to see here is a pie chart. So this is actually looking at our selection. In this case, I have a decent selection. I would say anything 50-50 or higher is good. We really want to see the water side, which is this one right here, doing with the majority of the work. And in this case, we do. We have a 60-40 split. And this is what this is your sensible capacity from the air side, just the air handler, and then the sensible capacity taken care of by your hydronic water coil. So we really want the water coil to be doing the bulk of the work. And 60-40 is a decent selection. I would say a more aggressive selection would be up to 25% on the air side, 75 on the water side. But that can be a little bit more of a challenge to get to depending on your room conditions. You need a pretty high SHR, sensible heat ratio. It really takes a high sensible ratio compared to your latent loads to get there. So it depends on your space conditions. How many occupants do you have? How much latent load compared to the sensible load are you going to see in that space? This is a good way to kind of check and make sure I'm on track. I'm not creating a system with expensive diffusers that I'm not actually using the water coil on. So just another metric to kind of give you a good thumbs up and see if you're in the right direction on your selection. All right, so that's the bulk of this software. There's a couple more features we'll talk about, and we'll run into a selection, a quick example on selecting these. Last thing I would like to point out is your estimation schedule. This is actually if you have a bunch of zones, maybe you have 100, 200 zones even, and you've run all the selections, you have a bunch of different beams selected. You can actually use that estimation schedule to trend that down, and it's gonna delete the inlet sizes, the nozzle sizes. It's gonna give you beams that are similar in price, and it's gonna consolidate. If you have 100 beams selected, it can drop that down to 5 beams in a bunch of different quantities and help you get a budget number. So that's also another feature to use. So we'll quickly jump into that. Again, another reminder. So in this case, I had 3 lines selected. It's combined zone 1 and zone 3 because they're the same length of beam. They're both 4-foot chilled beams. So in this case, I only have 2. It's dropped 1 line. So that can be a good way to give a quick budget price. If you're not finalized on your drawings, and maybe it's 50% design, you can check this and get a budget and see if you're on track within your budget. So back to our selections. Again, you also have the export all-in-one line strings here for the sales side of things. That helps keep the information together as we go in and output these in our pricing software. We also have a throw data cell here, and we can go back to the input form. But one word of caution, if you use this after you're already in here, you are going to lose your data once you come back into it. So I would not do this unless you want to start over on a project. So let's check out the throw data real quick. This is a page that you're going to find all the throw links at 150 feet per minute, 100 feet per minute, 50. It's going to have each individual zone. And then if you want to dig into one, let's select this middle zone here. It's a little bit longer throws. But I'm going to go into my room dimension review button here. So that's going to show me a couple of different items. The one on the left side is how far the beam is from the wall. And the one on the right side is looking at between beams, how much space do I need? And this is just to make sure that we are staying below 55 to 65 feet per minute at the occupied zone. You don't have that draft condition. A little bit high on this side, so maybe I can drop this to or add some distance from the wall up to 8 feet. Now I'm at 61 feet per minute. Just to get down in the 50s, I'm gonna move that beam a little bit farther from the wall. Also, this is probably a little bit farther than it needs to be. It could be a little bit tighter if you need that space. So you can decrease this one actually, would get us there. So essentially what I'm seeing with this particular selection is that 9 feet from the wall, I'm good, and 6 feet from the other beams, I'm gonna have a good, I'm not gonna have a draft below the chilled beams. So that's a good way to go back and check these spaces if you wanna do that. All right, so backing up into the selections, I think we'll jump out of this and actually do a quick example. If you want to take a peek and follow along with this, you can open up your version of the software if you wanted to download a copy from our website. Also, there is a PDF in the GoToWebinar app you can take a peek at. That's where we're going to start at here. So I'm going to go back to that PDF. So here's our layout examples. This is what you'll see in that PDF. It's a couple pages. We'll just talk about the first one here, but if you wanted to run a second, once we walk through this, I'll show you what I would do in this scenario. You can do the second exercise on your own if you would like to. So what we have is the first page. We'll start with this page and look at a couple zones and kind of think about the process of laying chilled beams out and see what that takes. And the second page here is related to the first page. All the different zones. I listed the sensible loads in that space, the latent loads, and the ventilation requirement. So I see this first zone. This is going to be on the top left here. It's a small office space. Let's jump right into that and see what happens. I've got 5,500 BTUs per hour. My sensible requirements, my latent requirements are 800 BTUs, maybe 4 people. Then my ventilation requirements are 26 CFM. So not a lot of CFM there. So let's go back. We'll take these loads and jump into our software that we've been using. I'm going to clear out these two, and we'll just focus on one at a time here. So I've got 5,500 CFM, or sorry, BTUs, sensible BTUs. I've got 800 BTUs of latent capacity. I did not list a heating condition, so you could use heating. This is telling me I actually need 87. So if I put in 26, it's gonna throw an error and ask me to change that back because I'm currently looking for 87 CFM. But so 26 is just not going to cut it. And the reason that's higher is because I have too much moisture in my airflow. So what this tells me is the latent load is driving the space airflow up. So let's delete this 5,500 and see what happens. Still at 87. So that actually did not have any impact on the sensible load in that space. So I need 87 CFM to treat my 800 BTUs of latent energy that I need to take out of that space and dehumidify some. So that's already done some thinking. I'm not able to get the minimum ventilation at this requirement or at these conditions. Maybe I do have some air handler. I can change my air handler. I have not ordered it yet. I can drop the wet bulb on that a little bit. You can see I dropped 10%. I'm down from 51.6 in the wet bulb to 49.9. And I've actually lost. I was at 87 before. Now I'm 19 CFM lower. Let's drop that even further. Let's see what we got to get to get to our minimum ventilation requirement. So 40%, I'm getting closer, but that's an incredibly low percentage or very dry air coming in. So 26 is what I was looking for. I'm at 27. The problem is my dew point on that air handler is 27.8. So I don't think that's actually achievable. That's lower than what would be possible. So what that tells me is with these given conditions, 800 BTUs latent, I cannot get to minimum ventilation in this zone. So with chill beams, we want to be as close to minimum as possible. We're not always going to get there. So 35% humidity at 55 degrees is kind of a ridiculous number. So we'll go back to 80% and a more realistic wet bulb temperature from the air handler. So 87. So that's not going to work out. I can't dry out the air enough to get there. So my other option is to go back and add some airflow to the chilled beam. But I'm actually already meeting that on this side. I bet the original selection, it would default to 50 CFM. So in that case, I would not be meeting the 87. So let's just put in 90 because it's telling me that I need 87. I'll round that up. So now that I've met my latent condition, I also need to meet my sensible condition. So we'll do that same exercise we just did. Or we could do that. We could jump from the GPM and have an iterative process. But I'm just going to go ahead and run an auto select. And actually, let's pick a couple more zones and do 3 at once here. So we're going to look at zone 1, zone 6, and zone 9. These are the 2 big ones, and then the top left zone. The others are very similar. We'll talk about zone 4 a little bit in the future as well. So looking at those 3, actually we'll add in zone 4. So 1, 4, 6, and 9. I'm going to go back into the second page. I've already put in zone 1. Zone 4, 6,000, 1,000, 115. So I'm just going to input these. Six in zone 9. 6,000, 1,000, 115. 109 is what it's telling me, so I need to be higher than that. In this case, I could meet the latent load even below my minimum ventilation requirement, so I have to add that CFM back in because that was higher than the 109 software thought I could get to that latent load at. So that's this space I'm actually going to be, I could actually get below my ventilation requirement compared to that first space where I could not. So that's an interesting thing to note there. Zone 6, 75,000, 12,000, so much larger space. I believe 220 was what my air was. So in this case, to meet that 12,000 BTUs of latent, I'm well above that 220 minimum ventilation requirement here in zone 6. So in that case, I won't put the 220 in because I need much more air at my given humidity levels. So zone 9 is the last one here, and we'll run a quick auto select. 55,000, 12,000, 150. And again, 150 is very low for that 12,000 BTUs, so we'll ignore that. And you can copy and paste in several areas. So we'll copy and paste that model side. I can do that because it's a green cell and it's changeable. I got a lot of red here, so I'm going to run my auto select. Instead of going through each line individually, run this quick auto select and we'll let the program do some thinking for me. So all lines found a solution. That's good. Not always the case. So you can see here I've got one beam, and these last two zones each have 5 beams, with the zone 6 being 9-footers, and zone 9 being 8-foot beams. So let's look at zone 9 and see. My next question here would be: do 5, 9, or 8-foot beams fit in this room? So I'll go to my PowerPoint, do a quick layout. So we're looking at zone 9. I've already got 4 beams in here from a previous exercise. You can do this a few different ways. So we'll start with 1 beam. So these are 8-footers here. I'm actually going to lay this out. There's a few ways you can do this. One thing I like to look at is where is my south-facing wall. I like to blow air on the south-facing wall. Try to take care of some of that envelope load with the beams wherever possible. So that's my thought process in laying it out horizontally. You can absolutely lay it out vertically here as well, but that's just one thing I would like to think about is where are my zones, where are my throws going to be the most helpful. So we need 5 of these. And I can already tell, but I have a lot of free space. Let's move this zone here. I have a lot of free space. So in some cases, if you have like a data center, we get a question quite a bit about can we use chill beams in data centers? We're trying to get some energy efficiency and treat those very dense loads. And in my experience, it's actually been very difficult to make that work because chill beams are designed to be low volume systems. And also you don't always want to have water up above the data center server racks and some sensible equipment like that, just in case you spring a leak, or you won't likely have any condensation, but you could have a leaking scenario. So that's one thing we typically see people avoid. The point there is you can't have some load densities that are too high for chilled beams, and you run out of ceiling space. So for example, in zone 8 here, a smaller zone, maybe I have a 50 or 75 BTUs per square foot. That's going to require a lot of chilled beams, and I actually may not be able to fit. So let's do a quick example and see. So for example, going back to just some quick math, maybe my area on this is a 20 by 20 room, and I'm making some assumptions. This may not be accurate. 20 by 20 space, and I'm going to use 100 BTUs per square foot, which is very high. I would say most scenarios you're going to see about 15 to 35 BTUs per square foot. So length, width, BTU per square foot. And given those parameters, my total sensible load in the space would be the area times the BTUs per square foot. This times this. So I need 40,000 BTUs in that room. So I go back and let's run a quick selection, see what happens. 40,000 sensible. If you have a load density that high, you probably don't have to worry about latent. It's probably going to be a very sensibly driven space. Not always the case though, so you can definitely check that. So auto select. So to meet that 40,000 BTU space load, I'm looking for 3 8-foot chilled beams. So let's take that selection and go back, assuming maybe that was the server room. It's a very, very low dense space. 3 8-foot chilled beams. So here's my 8-foots that I had created earlier. And let's see if we can drag 3 of these in here. And sure, I've got enough space, but I'm seeing a problem where these beams are very close together. So in this scenario, if I had a load density that high, I'm actually not going to be able to comfortably fit out that room with 3 8-foot chilled beams. You really don't want to have this many active chill beams close together. So in some spaces, like a server room, you have too high of a load density, and we actually can't get enough beams in the ceiling to treat that load. So that's a challenge in some spaces. Maybe you have a lot of glazing, a lot of solar gain. You don't have a high enough U value on your windows. That could cause some issues. But generally, if you're anywhere from 20 BTUs per square foot up to 50, you're probably okay. I would say 35 is kind of the middle of the road that we see pretty often. And that may even be high for many applications. So in this other case, zone 9, we're actually nowhere near that level of density. We're comfortably able to fit 5 to 8-foot chilled beams in here. So that checks out. And generally you want to see the beams in the middle of the space. You just want to throw, excuse me, if it's a two-way discharge, you want to throw against both walls from the center. You also could turn each one of these horizontally or vertically. The difference here is now I got to go back and look at my throws. I'm throwing at each beam. I want to make sure I've got enough space between these to make sure I'm not going to have a draft condition right below. Maybe this is an open office. There's a bunch of people with papers in their desks. I don't want to blow those papers around. So that's another reason I like to have these in line with each other and not throwing at each other. You can see above I actually have a few beams in this first, or the zone 6 here. So let's take a quick look at our selection that we just did for zone 6. So I got 75,000 BTUs. I'm meeting that. I'm also getting my latent load condition met. I've got 5 chilled beams, and they're all 9-foot chilled beams. So 45-foot chilled beam. And you can see that's actually quite a bit higher if I was going to look at my BTUs per lineal foot. I've got 75,000 divided by 45 feet. So let's see what we're getting out of that actually, for the sake of curiosity. 75,000 divided by 45 foot of chilled beam. So I mentioned earlier that 1,000 BTUs per lineal foot was pretty common, a good starting point. In this case, we're actually up to 1,600, so we're pretty high. That's a pretty load dense chilled beam, which is a good selection. And I can verify that by looking at our building summary. We're still above 50-50, but we actually have gone down a little bit. And that's because we have a lot of latent load here. All right, so looking back at that zone 6, we've got 5 9-foot chilled beams. And in this case, I've laid these out close to the center of the room and one in the middle. If I put this guy here, I may have draft conditions between these two, so I like to stagger it whenever possible. Again, there's no problem with going vertical and washing the windows on the side. That actually may be a better selection just because you want to limit your draft conditions. One side note about active chilled beams is that there is less draft potential with this product. That's because we're supplying 55-degree airflow to the chill beam. We're actually going to be inducing the 75 room air through that water coil before we're actually going into the space. So generally we're discharging, actually let's go take a look. What are we discharging our temperatures over here? So on the air side, we're going to look at my discharge air temperatures. So we're into the 60s, up into the mid 60s on one of these, on every single one of these beams, even though we're giving it 55 degrees on the entering air side. So you have a comfort benefit there where you're not going to feel that draft even at higher velocities. So that's actually a comfort benefit where you don't have to worry about drafts quite as much because you are discharging warmer temperatures from the chill beam into the space, even though you're still supplying that cold 55-degree airflow to the beam. So side note I like to point out when talking about how these work. So the next example we want to take a peek at is this conference room. So here I've done another selection. This is zone 4 we looked at. In this case, I'm actually not using the ACBL, the two-way discharge chilled beam. So zone 4, we'll close back over here. In this case, we have a 4-sided room, obviously. So we've got a couple beams on the perimeter. So let's change that model type and see what happens. Am I able to get away with these 3 beams in that area? So zone 4, this is my second line here. I'm going to change, now I don't have the ACBL. I originally needed 1 4-foot ACBL. But let's drop this down to ACBRs and see what I can do with ACBRs. Or let's actually bump this load up a little bit. 6,000 is probably a little bit light. Maybe you have 10 people in that space. You need 20,000 BTUs of sensible and maybe 4,000 BTUs of latent energy. Let's run that auto select again and see what we can get away with. Yeah. So in this case, I ran an auto select. I need 115 CFM. I'm actually well above that, but I'm still not meeting my laden loads. So what I'm going to do, the auto select met my sensible capacity, didn't quite meet my laden load, so I do need to go back and touch that up. Let's add 5 CFM per beam. Again, there's 3 beams, so that's going to be 15 CFM for the zone. And see if that meets our laden. It does not quite get us there. Let's bump it up a little bit more, 125 per beam, 150 per beam, and just keep bumping that up until we meet our laden loads. And there we go. I'm going to back up down just a little bit, actually. Get a little bit closer to our design. So there we go, 145, right on the 4,000 BTUs of laden. So I had to add a little bit of CFM to take care of that laden load. Now I'm actually overcooling space a little bit. So I'm able to get away with less GPM because I needed that airflow. So now we're a little bit closer. I dropped it down to 0.5 GPM, which is kind of the minimum we like to operate in. Typically, we like to see 1 GPM or more because that's where the water is going to be turbulent. We want to get as much energy out of that water coil as we can. So 0.5 is on the lower end, but we don't need that capacity here, so it's going to be all right. We're still over our sensible load a little bit. But I needed 3 7-foot ACBRs. And just to remind you what that looks like, that is as this beam. In this case, you can install it horizontally, discharging horizontally, or discharging vertically downwards or upwards. And the mounting brackets will change. So in this case, I would want to do it vertically down and not blow across the room. So for this layout, I did need 3 7-foot chilled beams. So that's 21 foot of chilled beams. Luckily, I have 3 clear walls, and I can avoid the door if I need to. And this is how I would lay out this conference room if you have a lot of load in that space. So that's looking at another conference room. Those can be tricky. Beams are not always great at modulating your airflows a lot. For example, the VV system, you may have a 10-to-1 turn down. With a chill beam system, you're probably closer to 2-to-1. And if you're clever and have a couple of VAVs in that space, you could get up to 4-to-1. But I would typically see a 2-to-1 turn down with chilled beams, active chilled beams. So let's go look and see what I can actually get away with there. So my total airflow is 435. I'm supplying 115 CFM. How low can I turn that beam down before I get to the 0.2 inches of static? Another option over here on the right is going to be the minimum VAV requirements. So my total discharge, again, I was supplying 115 to this zone. My total discharge is actually 525. That's because I have an induction ratio of 2.6. So I'm inducing a lot of airflow through that water coil. I'm well above 30 or 40 BTUs per CFM transfer effectiveness. So decent selection. And I'm actually going to be able to turn that down from 115 down to 84. It's not a huge turn down. It's because we have a higher nozzle. So you don't get quite the same amount of turn down there. So 84 is going to be where we're going to start losing the induction process of the beam. And maybe you're in an unoccupied mode. That's not a big deal. You're not worried about dumping. This beam is a vertically discharging beam anyway, but we don't know how much is going through the water coil once we get below that 0.2. But if you're unoccupied, the space is well within the deadband or close to your set point in that space. You may not need any cooling. So you can turn down further if you want to have a system that works that way. So the sequence is going to allow you to do a lot there and turn down the airflow while still maintaining a comfortable space condition. So 84 is the minimum we would typically recommend for an occupied space, but if you wanted to have an unoccupied mode, you can go lower than that, but these are the values that we typically would stop at for occupied space conditions. And just to kind of reiterate that point, we do like to see VAVs used with chilled beams and have some variation in your airflows, but you won't get the same swing that you would expect with an all-air system. But that is a great way to make sure you have a very efficient system, and you don't always need to be at 100% design on your CFM. You do not need to have a constant volume system. You can vary both the CFM and the GPM on the chilled beams as well. So last point here, we'll actually do one more quick selection. Let's go back to our building summary. We're a little bit lower. Let's do another selection just to see if we can get that up higher. Now I'm going to do an auto select on all of these zones with primary airflow as my target. So I want to reduce my primary airflow as much as I can and see where I end up. So I'm not meeting my sensible load here, or latent load, sorry. Let's pump that back up, make sure we satisfy that space condition. Getting closer. Too far. All right, so there we go. So now let's see what the building summary says. I ran the auto-select. The only difference between this selection is the first one was quantity, and the second one is primary airflow. So we're trying to target, instead of first cost with the quantity, less beams to hang, less connections to make, less coils to sweat together. Now we have a little bit more beams. The quantity is going to go up, but our CFMs have gone down. And I got a little bit more capacity back out of that. So I was at 54% on the water side before, now I'm at 58%. So that's one way to get a little bit more out of the system. And what's driving this is really your latent loads in the space. So if your SHR was lower, that would it would look better. But that is how you can validate you have a pretty decent selection. And there's no red flags essentially on do you have an expensive diffuser system. So last example here, we're actually going to go back and we're going to take a look at all these zones. And what you can do, what I've done in this example data here, I've taken all of those loads and I've copied them into a chart, and then I copied them into another section in Excel that matches the formatting of the selection software. So what that allows me to do is I can have all my zones listed here. I can fiddle with these requirements. I can copy and paste all of this in directly to the selection software. So I'll go back. I just copied it. I would recommend pasting as values because there's a lot going on behind the scenes. You don't want to overwrite the formulas that are working in each of these cells. So just paste values, and that'll keep all the formatting behind it. I've got some existing quantities from my previous selections. I'm just going to delete that, and it'll. I didn't like that actually, so I've crashed Excel. It looks like. So we're going to start over with a fresh copy. All right. Every now and then, doesn't like to work with us. Okay, and we're back with Excel, so that's good. Backing up, actually, I can still do the same thing in this page. What I was doing there before we lost that Excel selection was I was copying and pasting directly from my my project file here. I have again formatted this in the exact arrangement that we have in the software, so I can copy and paste all these values in. And we're going to paste as values. So if you already knew these values, you have the schedule you're taking off. You can't actually do it here, throw in the models, or you can do it from the other selection. You can go ahead and go back into the go to performance. I'm going to go ahead and put these in. If I want to get even more advanced, I like my links. I know what my baseline CFMs are going to be. Or I wanted to switch to a 4-pipe selection, I could do all that here as well. And then we'll just hit go to performance, and we are going to push this right back into the software. So if you are able to lay this out into to Excel in the same arrangement as these fields right here, they'll come right in. You're already ready to hit a quick auto select. It's going to think through, take care of all these red cells, and make sure you're meeting all your design conditions. There we go. So essentially, if I'm ready, I have everything formatted. You can run this selection very quickly. There's one zone here I left in to keep this red. I'm not quite meeting my latent load that I wanted to see. And again, just to kind of reiterate the points from before, I can go back and drop my primary air conditions. But in this case, usually that's all the other zones are meeting their latent capacities. So I don't want to select the air handler just around one zone. So in this case, I'm just going to add some airflow back to that space. So let's add some CFM until we get up to 12,000 that we need to be at. There we go. We're still just a little bit below, but not very far. So that's pretty close to being a right on selection. So now I'm done. That was a very quick exercise. If you have everything laid out per zone, you know your latent loads, your sensible loads, and your outside air conditions, or outside air conditions and your minimum ventilation requirements. That's all you need to do to run a quick auto select.
Hey, Nathan, got a question here from Matt. Is there any logic behind doing this process before selecting an air handling unit?
Yeah, that's a great question. That's absolutely our preference. Whenever possible, we do like to see these done first. So you want to start from the zone level, back that out, see how much airflow you have, and kind of dial in and get those details worked out at the zone level. Otherwise, if you start with your air handler selection, you may be backing yourself into a corner where maybe you oversized too much and you could have had a more efficient selection, or you've undersized it and actually you needed more capacity out of your beams and had to add some airflow back. So we definitely prefer to start with the software and the zone level selections, get that train trace running and to get as much resolution out of it as you can per zone, and base all of that, the equipment selections around what the beams need to see. So that's absolutely, we recommend starting that way. We realize it's not always possible. Maybe you're doing a retrofit and you're kind of locked into your equipment. You have to work around those parameters, but the ideal scenario is that you start with the chill beam software, zone level selections, and you back that up to the equipment level and select your equipment level around your space needs at that point. So great question. That's the process we would recommend. So with that wraps up the software section here and that layout example. I think we're going to take a quick break and maybe reconvene after lunch. Any more questions in the meantime that you guys see? So I believe we're a little bit ahead of schedule today, but we'll reconvene at 1 o'clock.
All right, thanks, Nathan. It does look like we actually ran a little short here this morning, finished up early. So hopefully that gives everyone on the line here a little bit of time to catch up on work and everything like that. And we'll take a couple minutes here and keep this on. If you have any questions about anything that we talked about this morning, we can address those now. We'll take about 5 to 10 minutes and see if any questions come in. I do see that we actually already have a question here from Mitchell. Is there a section in this tool that shows the max CFM per beam with applicable nozzle size?
Great question there. There's not actually a tool that tells you exactly that. What we would look at, there's going to be a few parameters that affect that value, and you'd have to go through and kind of iterate to find that exact number. And it really depends on what you are able to allow in the space, what noise levels you're comfortable with. For example, this guy is pretty loud here. That's going to be driving your airflow. So it's if you're able to have more noisy space, it's going to be a different CFM. If you need a quieter space, it's going to be a much lower CFM. And then also your static pressure that you're able to hit. If maybe you don't have the right pressure available, that's going to limit you as well. So it's kind of a case-by-case scenario. There's no real hard rule that you can only get so much air through a chill beam, but you're going to have some trade-offs once you start adding CFM back to that beam. And those trade-offs are pressure and noise. Great question.
Nathan, you may have already talked about this, but is there a rule of thumb for how much CFM roughly you can get per linear foot out of a chilled beam?
Yeah, a quick rule of thumb for that would be anywhere from 3 to I'd say 30 CFM per linear foot. Once you get much over that range, it can get kind of loud or higher pressure. But again, it's kind of case by case and what you're able to allow in that space. Yeah, another good question.
Sent to you. You'll have to log into that link at right around 1 o'clock is when we'll be starting this afternoon. So hopefully this finishing up early gives everyone a chance to kind of reset and maybe catch up on some work here over the next hour and a half. And we will be back at 1 o'clock to start the afternoon session. Thank you, everyone.